In this paper, we introduce a method known as weight distillation for transferring the parameters of a teacher model directly to a student model. This technique eliminates the need for additional learning during parameter transfer, thereby accelerating the training process. We demonstrate that the function used to map parent to destination parameters can be as simple as cloning with minor modifications. We also employ weight sharing and SuperNet training to reduce the engineering and GPU resource costs associated with architecture selection. During each training iteration, subnets are randomly selected, effectively increasing the number of training epochs for each subnet. However, it's important to note that SuperNet training generally requires more training time compared to standard network training. In our approach, we selectively reduce the model size by making some weight parameters zero, a process known as pruning. We focus on structured pruning, which involves extracting a smaller subnetwork from a pre-trained model and fine-tuning it. We introduce a neuron ordering method to ensure consistency across all transformer layers. This method is a solution to a constrained pruning problem, where the number and index of preserved neurons must remain consistent across all transformer layers. Our emphasis is on achieving faster training within a reduced number of epochs, rather than striving for higher accuracy through extended training periods. We propose a method to assess the importance of neurons consistently across all transformer layers. We compute the average magnitude of each neuron's output and rank them based on their importance. This neuron ordering method ensures that the most important neurons are included in the destination network, aiding in determining the most suitable weights for initialization. For each block of the parent model, we sample a portion of its weights, biases, and normalization parameters to initialize the corresponding block of the destination model. When subcloning matrices from the parent to the destination network, we maintain the standard deviation of the parent layer's neuron outputs in the destination layer. We multiply the subcloned weights by a factor that represents the ratio of the embedding sizes for the parent and destination networks. This scaling is unnecessary for the parameters of layer_norm and batch_norm layers, as well as the bias parameters of the linear layer. We also remove a certain number of blocks from the pre-trained model to initialize the destination model, typically from the middle of the network. The destination network is initialized with fewer blocks and is not fine-tuned, yet it attains meaningful loss value.